This is the nephron. There are 1 million nephrons in the kidney that work to filter blood, control the concentration of salts in water, and regulate blood pressure and volume. Several nephrons, or 1 million in this case, are needed to efficiently and sufficiently get the job done. Each nephron is characterized by a series of folds and loops that the unwanted parts of the blood travel through. This is what causes the nephrons to be 40 miles in length when stretched out. The main parts of the nephron include the glomerulus, Bowman's capsule, proximal renal tubule, loop of Henle, distal renal tubule, and collecting ducts.
Urine is formed in the nephrons. The dirty blood enters the kidneys through the renal arteries and is quickly greeted by nearly 1 million nephrons in the renal cortex. The first part of the nephron that the blood is filtered through is the glomerulus. It is here that urea and anything else that is small enough filters out of the blood and into what will soon be urine. The Bowman's capsule collects whatever filters through the glomerulus. Next, the unwanted substances from the blood continue through the proximal renal tubule and then the loop of Henle, where the needed amounts of water and sodium and chloride ions are reabsorbed. Afterwards, the urine travels through the distal renal tubule and the urine will travel through the collecting ducts and into a calyx. All of the calyces then feed into the renal pelvis and the urine exits the kidney through the ureter and into the bladder. Finally, the urine exits the body through the urethra.
The glomerular filtration rate, or GFR, in both of the kidneys is about 125 milliliters a minute. This is 180 liters a day, which would equate to about 90 2-liter soda bottles. This value is extremely high, and it is obvious that we do not produce this much urine in one day. This is true because most of this fluid that is being filtered by the glomerulus is reclaimed. ADH, or antidiuretic hormone, controls water reabsorption in the body. It maintains water balance by acting to either increase or decrease water reabsorption in the loop of Henle and the collecting ducts of the kidney nephron.
If your body needs to conserve water due to a low blood water potential, the osmoreceptor cells in the hypothalamus will detect this and tell your pituitary gland to secrete more ADH. In addition to the increase in production of ADH, the hypothalamus will also send a message to your brain saying that you are thirsty. The ADH will then increase the permeability of the distal renal tubule and collecting duct, allowing more water to be reabsorbed into the blood vessels. Once the blood water potential returns to normal, ADH production will be reduced.
If your body needs to get rid of water due to a high blood water potential, the osmoreceptor cells in the hypothalamus will detect this and tell your pituitary gland to secrete less ADH. This dramatic decrease in ADH production will make the distal renal tubule and collecting duct impermeable, allowing no water to be reabsorbed into the blood and more water to exit the body as urine. Once the blood water potential returns to normal, ADH production will return to normal as well.
The ADH feedback loop is an example of a negative feedback because once the blood water potential returns to normal, the production of ADH is returned to normal as well. Blood ADH levels would be higher than normal in a person who just completed a 3-mile run without drinking any water because they would need to stop urinating and hold on to the precious water that they have left. This individual most likely lost a lot of water through sweating and normal cell function during exercise, and they need to replenish their water supply.
On Bill's 40th birthday, his friends threw him a summer picnic to celebrate. It was 100 degrees out, and Bill spent most of his day playing football and chasing around his kids. In order to cool off, he drank several beers and was running to the bathroom to pee very frequently.
Alcohol that Bill consumed directly inhibited the production of ADH in his body due to the fact that alcohol travels directly to your brain when you consume it. The insufficient level of ADH in his body led to constant urination due to impermeability in the distal tubule and collecting ducts. This means that no water was reabsorbed back into Bill's blood at all, and was instead carried right out of his body, resulting in dehydration. To make matters worse, it was 100 degrees Fahrenheit outside, and Bill was physically active. It is safe to say that a substantial amount of water was lost through sweat as well.
The main rule of sweating is to cool the body down, and Bill's body was in desperate need of cooling down that day. Bill could have prevented his horrible hangover by replacing the cold beers with water.
Diuretics, aka water pills, help rid your body of unneeded salts and water, which help lower your blood pressure. They work by making your kidneys allow more sodium in your urine. This sodium will then be accompanied by water from your blood. Diuretics also cause walls of blood vessels to widen, allowing blood to flow easier, further contributing to lowering blood pressure.
When too much water enters cells, tissues swell with this excess water. To maintain the concentration gradient, excess water outside of the cell draws sodium from inside the cell out of it in an attempt to reestablish the concentration. Sodium levels inside the cells will drop, resulting in an electrolyte imbalance that was caused by drinking too much water. Sodium is needed to create an action potential and transmit a neural signal. With insufficient levels of sodium in the cells, this won't happen, resulting in the cell's inability to communicate with one another.
If there is not enough water inside the cell, the solution is considered hypotonic. In order to reestablish the concentration gradient, osmosis, or the movement of water across the semipermeable membrane from high to low concentration will take place until the solution is isotonic. Isotonic solution means that the concentration of water and solutes are equal and osmosis is no longer required.